Good afternoon, students. Welcome to today's lecture on fluid mechanics. Today is the second lecture where we're going to talk about potential flows. So we already talked about potential flows last week. I wasn't completely able to finish up, and I think at the end I actually said a few things which might have rather confused you. So I would like to spend the first, let's say, 10-15 minutes to review some of the slides and then to redo the material at the very end of last week again, because I said things which were not completely correct, or at least not ideally phrased. So let me switch to the slides from last week and let's quickly go through them. So we have here this basic problem which shows boundary layer on the surface of a body, in that case an airfoil again, and the outer flow. And we learned that potential flow is corresponds to what we called here the outer flow. And potential flow is always an irrotational flow, meaning a flow without vorticity, because all the vorticity is confined to the thin boundary layer. Potential flow is also often called ideal flow. Ideal flow because the flow where we neglect viscosity. If we neglect viscosity, that means we're fundamentally modifying the Navier-Stokes equation. We're dropping the second derivative in space, right? The Laplace term, the viscous term, which means that we cannot satisfy all boundary conditions at the wall. And at the wall, we would like to satisfy a boundary condition not allowing flow to go through the wall. That we still do, but we cannot satisfy the boundary condition of having no slip. So in potential flow, we have to accept that there's a tangential velocity to the wall, a non-zero tangential velocity. So it's a slip boundary condition. Yes, and that's what we do. These equations without viscous term are called the Euler equation. They maybe look a bit easier because they have one less term, but they're not really much easier to solve, because you still have this non-linear term on the left-hand side, which creates a lot of problems from a mathematical point of view. But when we introduced the potential, and last week we showed that potential can be introduced if the flow is irrotational, if vorticity is zero. So if we introduce this potential, we have the simple relation that the gradient of the potential is equal to the velocity vector. And we used the continuity equation. So the equation that divergence of the flow field must be zero, we use this equation to derive the Laplace equation for the potential. And that's the only equation we really have to solve for the flow potential. And once you have the potential, you also know the velocity field, you just take the gradient. We also showed that there's a very close relation between the potential function, the flow potential, and the stream function. Stream function is a function that we introduced in the second lecture of this course. And we saw that lines where the stream function is constant, so isolines of the stream function, that these are streamlines. And we understood here that equipotential lines, so lines where the potential is constant, are always perpendicular to each other. So streamlines and equipotential lines are perpendicular at any place, as long as the flow is irrotational. That's always the condition. And with the same assumption, we could also show that for potential flow, also a Laplace equation must be satisfied for the stream function. So we really have a duality between these two. Both satisfy a Laplace function. Mathematicians call these functions harmonic functions. Harmonic functions are functions which satisfy a Laplace equation, and both are built such that their isolines are perpendicular to each other. Huh? So you form like a grade of streamlines and equipotential lines. Very nice, geometrically appealing theory. We had this slide just to give us the operators in polar coordinates. And then we started looking at fundamental solutions. So instead of solving this Laplace equation for one particular flow field, for one particular object, we just looked at general solutions or fundamental solutions as they're called. We introduced a parallel flow. We saw it's a really simple, a linear function. We introduced a stagnation point flow, the ideal vortex, source and sink, and dipole. All of these flows satisfy the Laplace equation for the potential. We wrote down on the blackboard the potential function for that, and we wrote down the stream function for these fundamental solutions. And because these equations are linear equations, that means that every solution of a linear equation can be superimposed. So we can add up multiple of these fundamental solutions, and the sum of them will still be a solution. And that's about where we ended last week, and that's where I would like to pick up again. But let's quickly go through these fundamental solutions. Stagnation point flow, we'll actually look at this again in a few minutes later. We had the vortex, and the ideal vortex, so that's the vortex without vorticity, which has azimuthal velocity, which is decaying as we go away from the center, and it has a singularity in the center. So the point in the middle, strictly speaking, is not part of the flow field. It has to be excluded in a mathematical sense, because that's where the potential tends to infinity. It's or minus infinity. It's a log R function. And when we looked at, I think that's important to understand that and stress it again. When we looked at the streamlines here for the vortex, which are circles, and the equipotential lines, which are rays coming out of the center, we asked the question, so what happens if we exchange the two roles? If we take the stream function and make a potential out of it, and if we take the potential and make a stream function out of it. So we just switch roles. Geometrically speaking, that means the equipotential lines become streamlines, and the streamlines become equipotential lines. And that's then the source or the sink, right? Now the streamlines are rays coming out of the center of the origin, and the circles are equipotential lines. And again, the point in the center is a singularity. This is where you have a mass source coming out, and the strength of the potential of the source. We had the variable m for the strength, gave us the mass flow rate coming out of this source. And of course, if m is negative, everything goes back into the center. We have a sink. And then finally, I tried to show you on the blackboard what happens if we combine a source, something comes out, and a sink, something sucks everything in. And we give both equal strength. So that means everything that comes out locally will spread out with these rays, but somewhere where we have to sink, it will all disappear again. So every streamline coming out of the source will eventually disappear in the sink. And if we bring source and sink close together, in a mathematical sense, that means we bring them infinitesimally close together, we end up with a so-called dipole, which has these circular streamlines. So a source and a sink is also called a monopole, and two together, infinitesimally close, are a dipole. So these were the fundamental solutions we looked at. And then I quickly started with that. Then please forget what I said there because I said it in a well, I didn't say it wrong, but not in a meaningful way. So what this picture shows, I think last week I said it shows a dipole and a parallel flow, which is of course wrong. It even says it on the title. What this picture shows is what happens if we take the fundamental solution for a parallel flow and we add to it the fundamental solution for a source. So the source is located in the center at the origin here, and it creates velocities that are coming out at a certain strength m. The parallel flow is coming from left to right. And if we take the streamline here on the x-axis, coming from the left, we have the parallel flow with a constant velocity u. And from the right, or at least from where the source is located, we have a source flow coming out of the source in the opposite direction. And the farther away we get from the center of the source, the more this velocity decays. And there will be a point, and it's actually a point denoted by S here, where the velocity coming from the parallel flow and the velocity coming from the source exactly cancel each other. So we end up with a zero velocity, right? We are superimposing, we're adding up the two solutions. So this is stagnation point. And if you plot all the streamlines, which you can do easily, you just add up the two stream functions and plot the isolines, you will see that you obtain one streamline. This is thick black line, which goes exactly through the stagnation point. And you have a bunch of other streamlines which go around this streamline. And you have a few streamlines on the inside. If we go very close to the center, it looks very much like a source with radial streamlines coming out, which are then soon deflected by a parallel flow, such that they're all washed downstream. Now, in any potential flow, a streamline can also be understood as the surface of an object, right? Remember that in potential flow, we are accepting that we have tangential non-zero velocities on the surface of an object. So any streamline here, in that case here, the thick solid line, can be thought of as the wall of an object. So we can think of this as the leading edge of a blunt body, maybe the leading edge of a wing of an airfoil. And the streamlines here are streamlines going around this leading edge of the airfoil. And because we have the stream function now, or the potential, both work equally well, we can compute the local velocities. And if we can compute the local velocities, we can use Bernoulli's law, and we'll do this maybe in the second hour today, to compute the local pressures, because the local pressure will depend on the velocity, right? You remember from Bernoulli that if the velocity increases, the pressure will go down and vice versa. So we compute the velocity, and from the velocity we compute the pressure, so we can determine the pressure on the surface of that object. And that's the sketch on the right-hand side. So here again, this line is the surface of the object, or is this one particular streamline that we chose to be the surface of the object. And the arrows here indicate the pressure. So right here at the leading edge of the object, we have pressures pushing into the object, right? Because that's where, at the stagnation point, we're bringing the velocities to zero or close to zero. Right at the stagnation point, they're exactly zero. So all the velocity will be translated through Bernoulli into a pressure. So that's why we have a very high positive pressure at the stagnation point, and it's still a positive pressure, pressure surplus, as you go a bit further downstream. And then at this point, for this particular shape, it's at 113 degrees. The velocity, or you can see this here, the velocity increases or the flow is accelerated. So it's higher than the nominal velocity. So we have a negative pressure, negative relative to the ambient pressure. And you see here, P, the local pressure, minus P infinity. So here we have suction on the object. So we're sucking on the object. This a bit later on will be part of what is generating the lift. It's sucking the object. And of course, the positive pressures here are pressures which generate drag for the object. So this is how we will go about to compute lift and drag. So this is just one example of what you can do, maybe the easiest example. Taking the potential for parallel flow and adding to it the potential for a source. And you get this body. Now, if you follow these streamlines and go a bit further to the right on this sketch, you will see that these streamlines, they just open up more and more and more. So this leading edge body is infinitely large in downstream direction, which is not that useful. So because most objects, I mean, in reality, they're all finite size objects. Now, what you could do is you could add a bit further downstream a sink, so that all streamlines that come out of the source here at the origin will eventually, for the downstream, disappear into the sink again. This will have the effect that this streamline, this thick streamline, which we consider to be the surface of the body, is a closed streamline. It will close and we will have a closed object. So we have a source and a sink, and there will be a closed streamline around it. You can also think of this as in terms of mass conservation, it has to be like that, right? Nothing can go out because everything, whatever comes out here, must somewhere disappear there. Now, think again of how we did the dipole. If we bring the source and the sink infinitesimally close together, we still have a source and a sink, and we have these closed streamlines. If we add such a dipole to a parallel flow, we get the following solution. We can get the flow around a closed body, and the closed body is actually a circle, or if you think of it in 2D, it's actually, or in 3D, it's a cylinder. So simply the sum of the potential for a parallel flow with the potential for a dipole gives you the flow field, the rotational flow field, around the cylinder. And you can draw all these streamlines. And mathematically, it's quite simple to do, right? You just look up in a textbook or like in your slides, in your notes, what is the potential for the parallel flow? What is the potential for the dipole? You add them, and you can even modify the strength of the dipole, and you will get a larger cylinder if the dipole is stronger, or you get a smaller cylinder. And again, you can compute the velocities on the surface of the cylinder, and you can, from the velocities, compute the pressures, so you can compute things like lift and drag, maybe. Now, there's a little problem with drag, and I announced this a while ago already. If you look at the streamlines, you will find out that everything is quite symmetric, or not quite symmetric, it's fully symmetric. It's actually fully symmetric, not only with respect to the x-axis, so bottom and top, it's also symmetric with respect to the y-axis. So leading edge and trailing edge, or front side and back side of the sphere, they look perfectly symmetric. So if you have a stagnation point here, you will also have a stagnation point on the opposite side. That means if you have increased pressure pushing the cylinder in downstream direction, you will also have the same pressure force, but in opposite direction, pushing the cylinder in the opposite direction. So in these potential flows, drag for a closed body will always be zero. It's not just like that for the cylinder. You can show mathematically that for any closed object, drag is always zero, which is of course completely wrong, right? We all know that. And that is one of the big drawbacks of potential flow theory. It's very good to compute streamlines, at least on the upstream side. Very simple, very quick, but it's completely useless if you want to compute the drag of an object. And why is that? And we'll spend more time on that in 2 weeks. It has to do with the flow separation. And you remember flow separation? That's something we talked about in the context of boundary layers, where we have all of a sudden a zero velocity gradient on the surface of the boundary layer. It's these Faulkner-Scan boundary layers, and we start getting backflow on the surface of the wall. That's the separation point. So separation is a boundary layer phenomenon, and it will have an effect which is directly also affecting the outer flow field. So there we have an interaction between boundary layers and outer flow, which is not covered by the potential flow theory by itself. And that's the reason why potential flow by itself does not work, why we always need to combine it then with boundary layers. That's why we do both things and not just one thing of the two. Okay, so for drag, potential flow is not good, but it is very good for computing lift, which is also an important thing, right? If you want to compute the lift of an object. And as an example, what I'm showing you here is the flow around the cylinder. So the flow around the cylinder is the superposition of a parallel flow and the potential of a dipole. That gives us the flow around the cylinder. And we're completely free in terms of potential flow theory to add even more fundamental solutions. So one fundamental solution that we have not yet used in these examples is the ideal vortex. So what happens if we take this configuration, parallel flow plus dipole, and we add an ideal vortex solution at the center of this object? So we add something which rotates. That is actually modeling a cylinder which is rotating, right, as it's shown here. And depending on the strength of the vortex, we can increase the rotation or we can decrease the speed of rotation of the cylinder. And maybe some of you have heard about this effect. It's called the Magnus effect. It says that a rotating cylinder will generate lift. And why is that? Well, because if you have a rotation in these cases in clockwise direction, you will have a higher velocity on the upper side than on the lower side, right? On the lower side of the cylinder, the rotation velocity will go upstream, so will decrease the velocity, whereas on the upper side, it goes in the same direction as the parallel flow, so it increases the velocity. So we have a higher velocity on top and the lower velocity on the bottom, which then means from Bernoulli, we have a lower pressure here and a higher pressure here. So net will have a force pointing upward. And now comes really a beautiful thing. The strength of the vortex that we're adding, I hope you remember the strength, we called it gamma. Gamma was the thing we called circulation. Let me go back a few slides. So here we had the ideal vortex, and we defined gamma as the strength of the vortex, or actually it's the sum of all velocities along a curve around the object, around the cylinder. And if we know what this gamma is, or we impose the gamma, it can be shown, and this is an exact result for potential flow, that the lift force L is exactly equal to rho, density of the fluid, times U, the oncoming velocity of the parallel flow, times gamma. And this is an exact result. It's straightforward to derive it for the cylinder, but it's a bit more complex to show it, but it can also be shown that it's the case for any closed object. Any closed object, if you know what the circulation is, you can immediately compute the lift force. So it's a really beautiful theory, and that's where potential flow theory works really, really well. Okay, so that was the last slide, and it should have given you a bit of a better understanding of what's going on. So let me switch over to the slides for today's lecture. Just seeing there's a chat. Okay, Kai already answered it. Thank you, Kai. So let me switch to the new slides here. So second part, potential flow theory, and we're actually gonna go back a little bit. We're gonna go back a little bit and review that one slide that I just showed you before about this duality between potential and stream function. And we review the fact that both functions, potential and stream functions, both are satisfying the Laplace equation. Both are harmonic functions. And we remember that their isolines are perpendicular to each other. So you may now ask the question, well, if they're so similar, isn't there a nice theory to combine the two functions into one single function? And at least in 2 dimensions, and everything we do here now on the blackboard, on the slides, is just 2D, at least in 2 dimensions, this can be done. And it can be done through the theory of complex numbers. And what I'm going to introduce now is a thing called the complex potential. And it's nothing but an extension of the theory for potential and the theory for stream function by combining the two into one single function. And we will see that the real part of the complex potential corresponds to our classical potential, and the imaginary part of the complex potential is the stream function. That's how it's defined. It's actually quite straightforward to use, and that's why it's what its beauty is. So the complex potential, usually it's called W, is defined as the sum of the classical potential function plus the stream function for the same flow times I, where I is the complex number. So you can take the real part of W and you get the potential, or you can take the imaginary part and you have the stream. Now, this is a more or less arbitrary choice, but it's a very meaningful choice. And one meaningful thing is that if you take the derivative with respect to Z, Z is the complex variable, we'll come back to that in a second, you will get a formula, right? Taking the derivative gives you a formula. And if you take the real part of the formula, you have the velocity u. And if you take the imaginary part or minus the imaginary part, you get the velocity v. So in some sense, it's easier to work with. You don't have to look up all these formulas you have here on the top 2 lines. If you know the complex potential, you just take the derivative with respect to Z, and then you're there. You automatically have these velocities. Let me just quickly find my notes again, and then I'll show it to you on an example. So let me switch off the slides and go to the Blackboard. And let us look at an example here. And the example I'm making is a complex potential which looks very, very simple. It's a complex function. Maybe I need to turn on the light. Hold on a second. Yeah, I think it's a bit better, huh? WZ is equal to A being just an arbitrary constant times Z squared. Okay, so now I need to tell you what the Z is. Think of our coordinate system X, Y. This is our classical two-dimensional coordinate system. Now we just assume that this actually is like the real number. X is the real number, and Y is the imaginary number. So any point here for a certain X and a certain Y can also be written as the complex number Z equals X plus I, Y. Just another way of writing coordinates. Instead of saying coordinate X, Y, we just say it's the complex number Z, where the real part of Z is the coordinate X, and the imaginary part of Z is the coordinate Y. So what does this mean for this potential I just wrote down? So it's A, and Z is actually X plus I Y squared. And this is X squared plus 2I XY plus IY squared. Right? Let us group this together. Let us collect all the real valued, all the real valued and all the complex valued terms. So we have A times X squared. This term here is 2I XY. This is definitely complex valued. But this here, IY squared, this gives Y squared times I squared, and I squared is just defined as -1. Huh? I squared is equal to -1. This is the definition of the complex number. That's basic complex number theory. So the real part is X squared minus Y squared plus, now we take this term here, I A 2 XY. Okay, so what does our theory say? The real part of a complex potential is our classical potential, and the imaginary part is the stream function. So the real part, let me use color yellow for the real part. That's the real part. That would then be the potential. And the imaginary part would then be the stream function. So it tells us that this simple complex potential A times Z squared, you write it down again here, A times Z squared corresponds identically to the potential A times x squared minus y squared and the stream function 2a xy. So this is how we did it last week. Classical potential, classical stream function, and this is how we can do it if we have the complex potential. It's much, much shorter, much more compact. And I hope you recognize these functions here. This was one of the first potential flows that we looked at. This is the potential for the stagnation point flow, or the stream function for the stagnation point flow. So this is the flow. Maybe we can draw it up here. This is the flow which goes into a corner or into a stagnation point. You can either define it like that, or you can define it like that. And what else do we know? If we have the complex potential, then simply dw dz, so the derivative with respect to z, which is 2az, right? It's really easy to do, 2az. This is exactly equal to u minus iv. That's how the complex potential works. So again, the real part of this, the real part corresponds to the velocity u, and minus the imaginary part corresponds to the velocity v. Let's look at that. So 2az is just 2a x plus I y, or so fits 2a x plus I times 2a y. So it immediately follows that u is 2ax and v is minus 2ay. So there's nothing really new here. I mean, we had these results last week already. The only difference now is we got these results simply by looking at this complex potential and by simply taking the derivative with respect to z. So that's the power of the complex potential. It's a really elegant method, and it combines stream function and potential into one single function. And just by plugging in this definition for z equals x plus sine y, we can get the velocities and the potential. Now, this may all look a bit like magic to you, and it is a little bit of magic, I have to admit. But if you look at the theory of complex numbers, you will find that any function here, any so-called analytic function here, satisfies the Laplace equation. And I don't want to go through all of that on the blackboard because it creates a lot of writing, but it's basic complex number theory. Let me just go over here and write that down. So for any WZ, which is an analytic function, and I'll say in a few minutes what an analytic function means. For now, this z square is an analytic function. For instance, the sinus of z is analytic, cosine z. Many functions or exponential functions are analytic functions. So many functions are analytic functions. So for any analytic function, you can say that the real part of W satisfies the Laplace equation. And you can say the same thing for the imaginary part. Also, the imaginary part of any analytic function satisfies the Laplace equation. This is a fundamental property of any analytic complex function. This is something you can show if you go into complex number theory. Maybe some of you have heard of the Cauchy relations or the Cauchy equations. So the Cauchy equations, they show you that as long as the complex function is analytic, its real part and its imaginary part will always satisfy the Laplace equation. And that's why it is possible to say the real part is a potential and the imaginary part is a stream function, because they automatically satisfy the Laplace equation. Now, I need to tell you, what does it mean? What is an analytic function? And the longer explanation or shorter explanation, I just use the shorter explanation. An analytic function is differentiable in Z. It's a complex term for saying it is possible to take a unique derivative with respect to Z. So for instance, when we had W of Z equals Z squared, like what we had on the other side of the blackboard, of course we can take the derivative with respect to Z. For any polynomial, it's very easy to take the derivative. Hence, all polynomials are analytic functions. And because they're all analytic functions, the real part will satisfy the Laplace equation. Their imaginary part will satisfy the Laplace equation. And they can be thought of as potential and stream. What other functions are there? We have polynomials. We have like trigonometric functions. Like sine z, cosine z. Here we have z, z squared, z to the power of n. Exponential functions. They also are nicely differentiable everywhere. What about functions like a logarithm or a function like 1 over z? A logarithm. Well, logarithms are differentiable almost everywhere, except at the center. At 0, they go to infinity. So you cannot find a derivative for a logarithm at 0. So logarithms are actually analytic, except at z equals 0. Right? At z equals 0, logarithms have a singularity. The same is also for trigonometric functions like a tangent. Tangents also have singularities. Like at every pi, right? Periodically, every pi, they tend to plus or minus infinity. So they have local singularities, and that the singularities, they're not analytic functions, but everywhere else they are. So you see, it's a relatively, let's say, not so strict condition for a function to be analytic, which means that we can take almost any function we can think of, and wherever this function is differentiable, or we can also say wherever it has no singularity, it is analytic, and because it's analytic, its real part can be considered a potential, and its imaginary part can be considered a stream function. So that makes this whole theory of fundamental solutions much, much easier. We can just pick so many different variants of WZ, which are analytic, and all of them are in some sense fundamental solutions and describe some kind of flow, which then can be superimposed to create in combination more complex flows, like what we did before for the cylinder or for this leading edge body for this plumb. Okay, so it's a good time to take a break now. Let's take a break until a quarter past, and then we'll continue.